Hello everyone, this is He-In from UC Berkeley. Our topic is backward reachability using integral quadratic constraints for uncertain nonlinear systems. Backward reachability has been studied with several methods, including occupation measure-based method, Lyapunov-based method, and HJB-based method. A shortcoming of the existing method is that they rely on accurate system models. Only uncertain parameters have been addressed. However, in practice, there are many sources of uncertainty. Take the aircraft landing, for example. There is disturbance, such as the wind gust acting on the aircraft. There is also time delay and unmodeled dynamics acting on the actuator. In this paper, we propose a method to compute in approximations to the backward reachable set that are robust to a more general class of perturbations delta and L2 disturbance D. To achieve our goal, we merge dissipation inequality framework with integral quadratic constraints. We model the uncertain nonlinear system Fu of G and delta as an interconnection of the nominal system G and the perturbation delta. G has state xg, control U, disturbance D, and output V. Delta has input and output V and W. We assume the uncertain system is well posed. The disturbance has L2 norm bound R, and control constraint set is given as a polytope. For simplicity, in this presentation, we don't allow V to depend on U, but in the paper, V is allowed to depend on U in order to address actuator uncertainty. We denote xt as the target set for the uncertain system to reach at time t. The backward reachable set of xt for the uncertain system is a set of initial conditions whose successors can reach the target set at the terminal time with an admissible control. Our goal is to approximate the backward reachable set and synthesize a robust controller. The perturbation delta can represent various types of uncertainties and nonlinearities, including unmodeled dynamics, time delay, neural network, and gradient of convex functions. For each type of perturbation, there is an integral quadratic constraint to characterize it. Integral quadratic constraint captures the input-output relationship of delta. The input and output of delta are filtered through a system psi, and then a constraint associated with a matrix M is imposed on the output of psi. Therefore, integral quadratic constraint is parameterized by a filter psi and a matrix M. Psi is an LTI system with zero initial condition. We say a perturbation satisfies the hard IQC defined by psi and M if the integral of the quadratic term is non-negative for all time t. In the later analysis, we will replace delta by a filter psi and its corresponding IQC as shown in the figure. As mentioned above, the analysis on the original nonlinear system is instead performed on a new extended system, which is an interconnection of the nominal system G and the filter psi. With an additional constraint, delta satisfies the hard IQC. We define a combined state vector to gather states of G and psi. We write the dynamics of the new extended system as follows. In the paper, we look for a memoryless time-varying state feedback controller. By combining dissipation inequality with IQCs, we have the following theorem for backward reachability analysis. We look for a time-varying storage function V, a controller K such that the following condition hold. Then the intersection of the gamma sublevel set of the storage function at time 0 with the hyperplane xi equal to 0 is an approximation to the backward reachable set. We can see it by integrating the dissipation inequality in equation 3 over time horizon 0 to t. From delta satisfies the hard IQC, we know that this term is larger than 0. And from the assumption that L2 norm of D is bounded by R, we have if V of 0 is bounded by gamma, then V of t is bounded by gamma plus R squared. This basically means that if the initial condition starts from the gamma sublevel set of V, then its successor will not leave the gamma plus R squared sublevel set of V. By combining this condition with equation 8, we have that the terminal state will reach the target set And by combining 10 with 9, we have that the control signal derived from the controller K satisfies the control constraint. The following picture illustrates the main idea. The gamma plus R squared sublevel set of V is a funnel that bounds all the trajectories starting from the top base of the funnel. If the bottom base of the funnel is contained by the target set, then the top base of the funnel is the backward reachable set in approximation. Here we want to compare our method with HJB method. In HJB method, we solve for a value function V such that V dot equals to 0. So the computed backward reachable set is exact. But in our dissipation inequality framework, we search for a candidate of V that satisfies the dissipation inequality. Our framework has the merit of modularity. The inequality sign enables the considerations of IQCs and L2 disturbances. We can use sum of square programming to help us to search for V and K if we restrict ourselves to polynomial candidates. Equation 11 is bilinear in V and K. We can tackle the nonlinearity by alternating the search over them. In the optimization, M matrix in the IQC is also treated as a decision variable. Now let's look at a GTM example. The GTM is a 5.5% scaled commercial aircraft. We have its nominal longitudinal dynamics as follows. The control input is elevator deflection. We assume that there is an additive uncertainty acting on the actuator. So the actual control signal that goes to GTM equals to W plus U. We take the target set defined as a small circle around the origin. We assume delta is an uncertainty sector bounded by alpha and beta, meaning that delta of V can be any curve lying between the lines W equals to beta times V and W equals to alpha times V. We take degree 4 storage function to compute backward reachable set in approximations for time horizon 0 to 1 and 0 to 2. The backward reachable set in approximations are shown in the figure. The smaller one represents the in approximation for the time horizon 0 to 1, and the larger one represents the in approximation for the horizon 0 to 2. Some simulated state and control trajectories are also shown in the figures. As we can see that all the state trajectories reach the target set at the end of the time horizon. Besides hard IQC, we also incorporated soft IQCs in our method. Soft IQCs hold over the infinite time horizon. The reason why we need soft IQCs are as follows. First, the library of IQCs are usually provided in frequency domain and can always be translated into soft IQCs but not into hard IQCs. Secondly, usually the parameterization of the soft IQCs are less restrictive, which leads to a larger backward reachable set in approximation. Since soft IQC holds only on the infinite time horizon, they cannot be incorporated in the analysis based on the finite horizon dissipation inequality directly. So here, we use a lower bound for soft IQC. If delta satisfies a soft IQC, then the quadratic term has a lower bound that is valid over all finite horizons. This lower bound can be used in our finite horizon backward reachability analysis. Here, we slightly modify theorem 1. Now we assume that delta satisfies soft IQC, and we have an additional decision variable y22 that determines the lower bound. Now the intersection of gamma sublevel set of calligraphic V at time 0 with xi equal to 0 is an approximation, where calligraphic V equals to V plus the lower bound. Again, we can see it by integrating the dissipation inequality in equation 14. Using the lower bound for the quadratic term and the bound on the L2 norm of D, we have that the gamma plus R squared sublevel set of calligraphic V is acting as a funnel. To solve for V and K, we still alternate the search over them. Here comes the last example. we now assume the input perturbation is a time-invariant parametric uncertainty. This type of uncertainty can be represented using both hard and soft IQCs. As we can see, the M matrix for hard IQC is restricted to a smaller set than that of the soft IQC. And from the result, we can see that a larger backward reachable setting approximation is certified using the soft IQC. Conclusion. We proposed a method for computing robust inner approximations to the backward reachable set and robust control laws for uncertain nonlinear systems. We merged the dissipation inequality framework with IQCs, allowing for larger class of perturbations. We considered both soft and hard factorization of IQCs. The authors gratefully acknowledge support from ONR, Air Force, and NSF. Thanks a lot for your attention.